Good afternoon, everyone. I'm Ila Victoria, and in behalf of our group, me and my other group mates are going to report about the classification of geologic structures. You probably have a general concept of what a geologic structure is. The term probably brings to mind images of folds and faults. Perhaps you had the opportunity to take a field trip in where you saw some of these structures in the wild. We also had a brief introduction to this in our previous subject, Petroleum Engineering Orientation. These features are formed in response to pushes and pulls associated with the force that arise from the movement of tectonic plates or as a consequence of differential buoyancy between parts of the lithosphere. But what about the bedding in a sedimentary rock and flow banding in a rhyolite flow? Are these structures? And what about slump folds in debris flow? Are they structures? Well, technically, yes. But the link between their formation and plate motion is less obvious. So maybe we need to have a more general concept of what a geologic structure is. Now, what is a geologic structure? The most fundamental definition of a geologic structure is a geometric feature in rock whose shape, form, and distribution can be described. Basically, a geologic structure are characteristics formed in rocks caused by the disturbance from internal or external forces, such as powerful tectonic forces that occur within the earth and other forces that are related to the plate tectonic activity. Examples of geologic structures are folds, faults, joints, veins, cleavage, foliation, and lineations. Geologic structures such as faults and folds are the architecture of the Earth's crust. These influence the shape of the landscape, assess the degree of risk of landslide, bring old rocks to the surface, bury young rocks, trap petroleum and natural gas, shift during earthquakes, and channel fluids that create economic deposits of metals such as gold and silver. Folds and faults and other geologic structures accommodate large forces such as the stress of tectonic plates jostling against each other and smaller forces such as stress of gravity pulling on a steep mountainside. Understanding the structures and mechanisms that shape the Earth's crust can help you see when and where the crust was subjected to pushing or pulling. Folds and faults and other geologic structures accommodate large forces such as the stress of tectonic plates jostling against each other, and smaller forces such as the stress of gravity pulling on a steep mountainside. Understanding the structures and mechanisms that shape the Earth's crust can help you see when and where the crust was subjected to pulling or pulling. Let me emphasize myself. Geologic structures are features that are formed in response to pushes and pulls associated with the force that arise from the movement of tectonic plates or as a consequence of a differential buoyancy between parts of the lithosphere. From these definitions, it is obvious that there are several ways in which a geologic structure can be subdivided into groups. In other words, by necessity, there are several different yet equally valid classification schemes which can be used in organizing the description of geologic structure. For various purposes, different schemes are important. Consequently, there are many schemes for classification of these structures. At first, these various classification schemes may be very confusing. Thus, we recommend that you start by recognizing the basic geologic metric classes as the foundation of your understanding. Now, there are 7 main classification of geologic structures. First is classification based on geometry. Second, classification based on geologic significance. Third, classification based on timing formation. Fourth, classification based on the process of formation. Fifth, classification based on the mesoscopic cohesiveness during deformation. 6. Classification based on the strain significance. Last and seventh, classification based on the distribution of deformation and the volume of a rock. The first classification is classification based on geometry. This classification is based on the shape and form of a particular structure. There are three main classifications under this. It is the planar or subplanar surface, curviplanar surface, and the third one is a linear feature. A planar or subplanar surface. The planar components to be observed in the field include bedding, joints, faults, cleavage, and foliation. Now, this is an image of joints and beddings. A bedding is a primary layering in a sedimentary rock, formed during deposition manifested by changes in texture, color, and/or composition. A joint is a brittle fracture surface in the rocks along with which little or no displacement has occurred. It is where blocks move apart but do not slip each other. Next is a curviplanar surface. Now, this is an image that shows us a curviplanar surface. Linear feature. Linear components are less precisely definable, but they include the linear intersections of planes as well as linear elements sui generis. Sui generis basically means unique, having their own distinctive individuality as structures or textures of linear habit. Now, strip streak marks or on slick-sided faults or bedding planes and linear fabrics due to the parallel orientation of elongated crystals, xenoliths, or mineral groups are examples. Slick-sided can be used to determine the direction and sense of motion on a fault. All such linear features are commonly termed as lineations. But if the term is to be applied in this comprehensive way, it is obvious that it can, unless more particularly specified, have no precise structural significance, since lineations may form in so many ways, having different relationships to the overall form and origin of major structures. Moreover, the intersection of a planar structure or any chance plane observed in the field appears as a lineation. So it is also clear that careful study will be required in such a case to reveal its true geometrical significance. This subdivision represents perhaps the most basic classification scheme. In this scheme, we include the following classes of structures: joint, vein, fault, fold, shear zone, foliation, and lineation. Now let's talk about the joint. The joint is a fracture dividing rock into two sections that move away from each other. A joint does not involve shear displacement and forms when tensile stress reaches its first threshold. Next is the vein. The vein is a distinct sheet-like body of crystallized minerals within a rock. Veins form when mineral constituents carried by an aqueous solution within the rock mass are deposited through precipitation. So veins are commonly seen in rocks in nearby shores. Next, let's talk about fault. A fault is a planar structure or discontinuity in a volume of rock across which there has been a significant displacement as a result of rock mass movements. Next is the fold. A fold is a stack of originally planar surfaces, such as sedimentary strata. They are bent or curved during permanent deformation. Folds in rocks vary in size from microscopic crinkles to mountain-sized folds. They occur as single isolated folds or in periodic sets known as fold trains. Next is a shear zone. A shear zone is a zone in which shearing has occurred so that the rock mass is crushed and brecciated. A shear zone is the outcome of a fault where the displacement is not confined to a single fracture, but is distributed through a fault zone. Next is foliation. Foliation in geology refers to a repetitive layering in metamorphic rocks. Each layer can be as thin as a sheet of paper or over a meter in thickness. The word comes from Latin folio, meaning a leaf, and refers to the sheet-like planar structure. Lastly, we will talk about lineation. A lineation is any linear feature of or element in a rock. and can occur as a product of tectonic, mineralogical, sedimentary, or geomorphic processes. Lineations are the one-dimensional counterparts of foliations, and both are parts of the fabric geometric organization of features of a rock.
Classification based on geologic significance. Primary form as a consequence of the formation process of the rock itself. Local gravity driven formed due to slip down an inclined surface, slumping at any scale, driven by local excess gravitational potential. Local density inversion driven formed due to local lateral variation in rock density, causing local buoyancy force. Fluid pressure driven formed by injection of unconsolidated material due to sudden release of pressure. Tectonic formed due to lithosphere plate interaction due to regional interaction between the asthenosphere and the lithosphere. Due to crystal scale or lithosphere scale, gravitational potential energy, and the tendency of crust to achieve isostatic compensation. These four items in this scheme can be grouped as primary and non-tectonic structures. Note, it means that they are not directly related to the forces associated with moving plates. We purposely say can because in many circumstances, these categories of structure do form in association with tectonics activity. For example, gravity sliding may be triggered by tectonically generated seismicity, and the salt dome may be localized by movement of tectonic normal faults. Classification based on timing of formation. Since formational form at the same time as the material that will ultimately form the rock. Contemporaneous form before pole lithification but after initial disposition. Post formational form after the rock has fully formed as a consequence of phenomena not related to the immediate environment of rock formation.
Good day, everyone. My name is Brittany Servancia, and I will be talking about another classification of geologic structures, which is a classification based on the process of formation, that is, the deformation mechanism. This classification has four types. The first one is fracturing, which is related to development or coalescence of cracks in rock. Fracture just means the breaking up into pieces. This is a very important deformation mechanism in the upper part of the Earth's crust. There are two basic types, brittle and ductile fracture. In brittle fracture, there is no permanent deformation before the rock breaks. In ductile fracture, some permanent deformation does occur before it breaks. To distinguish these two easily, let's use this example of a reinforced concrete beam applied with force. As you can see, during a brittle failure, there is no crack or warning that something is wrong. In ductile mode, however, you can see cracks forming and propagating upward before the beam fails. Fracture is strongly dependent on confining pressure and the presence of fluids, but is not as strongly dependent on temperature. This means that very low temperature is equal to high differential stress. The next type of classification based on the process of formation is frictional sliding, which is related to the slip of one body of rock past another, or of grains past one another, both of which are resisted by friction. The third type is plasticity, which is resulting from deformation by the internal flow of crystals without loss of cohesion, or by non-frictional sliding of crystals past one another. Many years ago, after scientists have learned a fair amount about the atomic structure and bonding forces, they calculated the theoretical strengths of different materials according to Allmendinger. The strengths they predicted, however, turned out to be up to 5 orders of magnitude higher than what they actually observed in laboratory experiments. Thus, they hypothesized that crystals could not be perfect, but must have defects in them. The last type of classification based on the process of formation is diffusion, which is resulting from material transport, either solid state or assisted by a fluid, or dissolution. There are two types of diffusion: crystal lattice diffusion and grain boundary diffusion. In crystal lattice diffusion, this type is important only at high temperatures, such as temperatures similar to the Earth's mantle, because it occurs far too slowly at crustal temperatures. However, the grain boundary diffusion occurs at low temperatures, or lower temperatures, such as those found in the Earth's crust. As you can see at the illustration, note that the darker gray atoms have all moved from their original position by jumping into the adjacent vacancy. Atoms and vacancies diffuse in opposite directions.
The fifth classification is based on the mesoscopic cohesiveness during the formation. When we say mesoscopic, that is a scale that pertains to any structure that can be observed without the aid of the microscope on a hand specimen or a single outcrop. Geologic structures can be defined as brittle, ductile, or brittle/ductile. Can be considered as a brittle deformation if it is formed by loss of cohesion across a mesoscopic discrete surface. A cohesion is the ability of the particles to stick together. Next, ductile. If it is formed without loss of cohesion across a mesoscopic discrete surface. Now, you can see that brittle deformation is just the opposite of ductile. Lastly, it can be considered as brittle/ductile if it involves both brittle and ductile aspects. Based on the things that we've discussed in the previous slide, we can now conveniently consider the basic geometric classes of structures to be a manifestation of the mesoscopic cohesiveness of deformation. Manifestations of primarily brittle deformation include joints, veins, and certain types of faults. And manifestations of ductile deformation processes include cleavage, foliation, and folding. The scale of observation, in this case mesoscopic, is critical in the distinction between brittle and ductile deformation, because ductile deformation can involve microscopic scale fracturing and frictional sliding. Let's have a comparison on how brittle and ductile respond to stress. The first image shows brittle deformation. You can see here that there is a discontinuity in the layers of the stratum, in which the hanging wall has slipped down relative to the foot wall, and that is a sign of faulting. I believe that this is a dip-slip fault, mainly due to tensile stress. And because brittle deformation is more common in the upper part of the crust, there is a tendency for rocks to fracture, as very low temperature can result to higher differential stress. The second image shows ductile deformation. Folds are visible on the stratum. There are different types of folds here. It depends on which part of the stratum you're looking at. I can see anticline and syncline folds. And because ductile deformation is more common in the deeper part of the crust, rocks can flow, unlike in the brittle deformation. Also, ductile deformation is commonly a manifestation of plastic deformation and diffusion. The next classification is based on the strain significance. So, strain is the deformation of materials in response to stress, in which a reference frame, usually the Earth's surface, is defined as contractional, extensional, or strike-slip. So contractional, which means resulting in shortening of a region, from the word contract, which means to shorten. Next, extensional, which means resulting in lengthening of a region. Lastly, strike-slip, resulting from movement without either shortening or extension. So note that shortening in one direction can be, but does not have to be, accompanied by extension in a different direction, and vice versa. Also, regional deformation usually results in the vertical displacement of the Earth's surface, a component of deformation that is commonly overlooked. So the last classification is based on the distribution of deformation in a volume of rock. It may be continuous, penetrative, localized, or discrete. Continuous, meaning that it occurs through the rock body at all scales. Penetrative, it occurs throughout the rock body at the scale of observation, or up close, and there may be spaces between the structures. Localized means that it occurs only within a definable region, or certain region. Lastly, discrete. Structure occurs as an isolated feature, or detached from others. We have here an image showing the principal features of plate tectonics. Three types of plate boundaries arise from the relative movement of lithospheric plates, indicated by arrows on the image. The first is the convergent boundary. Convergent boundary is where plates collide. As you can see on the image, the arrows are moving towards each other. And we can also observe that there is subduction. So subduction zones occur when one or both of the tectonic plates are composed of oceanic crust. And during subduction, the oceanic crust is subducted beneath the continental crust as it is denser. And this oceanic crust is then recycled into the Earth's mantle. Next, the divergent boundary. It is where plates divide or move apart. Lastly, lateral slip or transform boundary. This is where plates are sliding past each other. A crust is neither created nor destroyed. So without these activities that arise from these plate movements, there will be no geologic structures. So here is the summary of the report. Brittle deformation is more common in the upper part of the crust, where temperatures and pressures are relatively low. It is a consequence of fracturing and frictional sliding. Next, ductile deformation is more common in the deeper part of the crust, because it is favored under conditions of greater pressure and temperature. Also, ductile deformation is commonly a manifestation of plastic deformation and diffusion. However, it is important to emphasize right from the start that different processes can act in the same places in the Earth. The processes that occur at any given time may reflect geologic variables such as strain rate, which is the rate of displacement in the rock body. For example, a sudden increase in strain rate may cause rock that is deforming in a ductile manner by folding to suddenly behave in a brittle manner by fracturing. Ultimately, most crustal structures are a consequence of plate tectonic activity. The forces that this motion generates, especially those from interactions at plate boundaries, produce the structures we study in the field and in the laboratory. The three types of plate motions are convergence, divergence, and lateral slip. Without the activity that arises from these plate motions, such as deformation, volcanism, and earthquakes, the Earth would be as dead as the moon. Here are reasons why we classify geologic structures. Geologists study rock structures for several reasons. First, they help us to understand the geological history of a region, and they also help us to understand the history of tectonic movements and plate movements. The analysis of folds, faults, and joints are all in a branch of geology called structural geology. And it is from these studies that we have learned about mountain building forces and have been able to interpret them in the light of plate tectonics. Second, the folds and faults and other geologic structures also help us to make geologic maps, which we use to infer underground structures where we can't see the rocks and to help us to understand the formation of geologic resources to locate and manage them. Like other geologic structures, folds and faults can be classified, and we learn from the classification that similar structures are formed by similar processes. By classifying the geologic structures and understanding how they are formed, we can learn to interpret the story left behind the rock. It is actually the geometry, the shape, size, the orientation of folds, faults, and joints that are essential to this interpretation. It's not only the geologic structures themselves, but it's also the erosional features, gaps in the geological record, that give us information about the geological history of a particular area. Remember, we can't understand continental deformation without understanding mountains. We can't understand mountains without understanding folding and faulting. We can't understand folding and faulting without understanding ductile and brittle deformation mechanisms at the atomic scale.